Thank you very much for the invitation. Yeah, and I'm so glad to have the opportunity here to share with you on the topic automatic organ design with large language model. Okay, and yeah, okay, I'm going to start. So I'm currently in Professor Qingfu Zhang's group, Optimal Group, based in Hong Kong, and most of the works conducted in this talk are joint work with members from this group. We have around like 20 PhD students and some postdocs and visiting scholars. Okay, so my talk has basically four parts and a conclusion. So in the first part, I'm going to have a brief overview of this emerging field, like automatic organ design using large language model. And then I'm going to introduce evolution of heuristics, which is a method for integrating large language model for automatic organ design. Then I'm going to present some case studies and also an open source platform named LFAD to like foster usage of maybe you guys who are interested in this area. Then in the last part, I will have an introduction on a preliminary attempt to fine-tune large language models for algorithm design. Okay, so in the first part, you know that in algorithm design are challenging in real-world applications. They usually demands expert knowledge and time-consuming try and error process with intensive manpower. So there's many like effort on automating algorithm design process. And now we have large language models. So here is a illustration of the progress and publications. I will not go into details. Okay, so we were thinking about that how to use large language models in algorithm design. So we first conducted a systematic survey of this research area. Basically, we collect around like 1,000 papers. Then we scan the papers according to our topic, which is algorithm design and optimization and like heuristic or like OR. Then finally, we got around 200 papers. Okay, so here is the number of publications with respect to months. Basically, we can see a fast increasing of publications, and most of them published on like top AI and EC conference and journals. Okay, so here's the university distribution and like country distribution. So we have like top universities and companies like Google and Huawei. They all working on this emerging direction. And here's a analysis of word clouds. So basically, we have some topics focusing on large language models, on fine-tune large language models, and some topics on optimization and combinatorial optimization, evolution optimization, and others. And here's like small, a comparative small area focus on science discovery. Okay, so when you look at the papers, you will find that the majority of papers use like pre-trained large language models. As illustrated in the left-hand side figure, most like about 80% of papers use pre-trained models, and here's the specific models they used. Like for example, GPT, DeepSeek, or others. And for the prompt engineering, different like prompt engineering techniques have been investigated. Uh, the most straightforward one is like zero shot, which means you only instruct large models for the algorithm design tasks without any examples. And also there are chain of thought reflection, in which in chain of thought, basically you tell large language models like to follow some steps, and uh, which can enhance its reasoning capability on the target task. And in reflection, you want large model to like make reflections on their responses to improve the results. Okay, so as you have see that there are many, like there's have a bunch of papers, and we want to make classification of these papers so that we can understand, and we can understand this research area, and also maybe provide some insights on future research. Then we classify those papers into four classes according to the role of large language models in these papers. So basically, we have the first class is large language model. Okay, so basically, we have three components in those algorithm design papers. We have a problem, we have an algorithm, and then we have the solution, right? And so for the first class, large language model as optimizers, LLMs are used inside algorithms to directly generate solutions. And usually they are used in an iterative manner. For example, if you can directly use large language model as easy operators to, maybe you can use it in like DE to generate new individuals, and maybe you can use it in like multi-object optimization, like for offspring generation. And then in the second category, large language models are used as predictors to predict the class, the category or the finish of a solution. This direction is like maybe like a surrogate model based methods. But we don't have to train the model, right? We have a pre-trained model at hand, and we directly prompt large language models to predict the performance. Then in the third class, we use large language models to generate embeddings of existing of the target problem and algorithms, which may enhance the algorithm design performance. Then in the last class, large language models are used as designers to directly design algorithms, which is a more straightforward way, more close to what human experts do in algorithm design. Okay, so in the first class, large language models are used as optimizer. Here's example. For example, in like traveling salesman problem, the solutions are like these kind of sequences. Then we give large language model the problem description and the existing solutions to instruct large language model to generate new individuals, new solutions, which is a new sequence. And in this case, because LLM has like pre-trained knowledge, so for some problems they can understand the description, and maybe they will like suggest some promising solutions when compared to conventional handcrafted and the hard operators. But like here are some representative works, some related works. There I would say that there are many words, and so we only like selected uh some of them. So basically, on left hand side is most uh like preliminary attempts as optimizers. Uh, and in the second word, like they try to use IAMs directly as optimizers in EC. Okay, so in this case, it not only use it for like for causal mutation, they also try to use LLM to select the parents to enhance the evolution algorithms. Okay, in the last one, LLMs are used for hyperparameter optimizer. And okay, here is one work on multi-object optimization. So basically, AMs are also used as optimizers, but in a multi-object optimization framework. So we first decompose them into several subproblems and let large language model to suggest new candidates. Okay, so the second class is as predictors. So in this example, we here we have a set of uh, candidate solutions and their fitness or their category. In this case, is the category better means a better solution, and worse means like not the solution not so good. So we then instruct large language models to predict in this in red one uh, whether it's better or worse, then LMs will suggest the category of the new individual. Okay, and here are two examples. In the first example, large language models are used as like both regressors and classifications, um, which is quite similar to the function of GP or surrogate made based on evolution optimization. And in the second example, multimodal large language models are used to predict the fitness of a car. Okay, so in traditionally we need to, when you have a shape, then if you want to know the performance of the shape, you need to do the simulation, computational simulation, which is expensive. And in this paper, they adopted a large language model to predict maybe the score of this shape, because usually human experts know what shape is good and what shapes are not so good, right? So basically, in this case, M can do some course prediction, then only the promising ones will be used in the actual simulation. In this case, they can speed up the optimization. Okay, so in the second class, we like use large language models as extractors. They are used to extract informations, which are usually hard for conventional model-based methods or other models. And for example, in this case, the structure the function is some structured informations are extracted by large language models on the target this function, and then those information will be used to capture the knowledge. And here are some more examples. In the second example, LMs are used to extract features for base optimization as like prior. Then in right hand side, LMs are used to extract the information of both the problem at hand and the algorithm for algorithm selection. Because conventionally we like we cannot let a model, maybe you train a simple algorithm selection neural network based on some features like some handcraft features. But in this case, because LMs can like understand the code directly, so they can have some like understandings of algorithm code then, which will help in the algorithm selection. Okay, in the last class, LMs are directly used as designers for algorithm design. So in this class, for example, here we give some problem description, then we have maybe one existing algorithms. Then we instruct large models to create a new algorithms modified by the given one. So in this case, will directly generate the algorithm description and the code for the target problem. Okay, so um, in this case, because has the code generation and task comprehension capability, so it differs from the traditional method, um, like parameter tuning or some simple function design. It can provide maybe new insights on target problem or generate like some novel algorithms. So along this direction, we have EOH, evolution of heuristics, which I will introduce in the next part, and fun search from Google, and also other works like Lamier by Nikki's group. Okay, so in the second part, I will introduce evolution of here EOH, the basic idea of EOH, and I think so basically it's like a evolution computational framework, which integrates large language models to directly design algorithms. Okay, and here is a, a pipeline or a timeline for the works along this line to use large language models as designers for automatic algorithm design. Um, we like we're around like like 3 years ago, maybe 2 years ago, we present some preliminary attempts, which is early version of UH. And then like 2 or 3 weeks later, Google published their fun search in Nature. And after that, our UH also got published. And there are some other like Lamia from Leiden. And also we have like the multi-object version of UH. And also Google, maybe 1 month ago, Google have their like Evo. I think many of you have heard of Evo. And actually, we also open sourced our platform named MFAD at end of last year. Okay, so basically, in UH and the works along this line, we can like we basically formulate the automatic algorithm design as searching or optimization in the algorithm space. Okay, so basically we have a set of instances and for the target problem, and we have an algorithm space. In other approaches, maybe the space is maybe for hyperparameter tuning, the space is a continuous or discrete space. Maybe in methods such as GP or others, the code can be a tree structure or some simple program. And in this direct like in our case, the algorithm can be more flexible. and complicated. It can be a code or even language. Okay. So then we have the performance metrics to evaluate the algorithm. For example, for TSP problem, we want to minimize the root length, right? And so the automatic algorithm design is a searching or optimization problem in the algorithm space to optimize the performance metrics. Okay, so then large language models in this case are used to operate in the large language and code space, which is difficult to formulate and very complex. And in this case, if we you may wonder that why don't we directly prompt large language models to generate the entire algorithms? Why don't we need to search, right? Because if you directly prompt large language models to generate the algorithm, it's like a random sample in the algorithm space, right? You don't so basically, in this manner, it is less efficient and usually will not have a very good performance algorithm on target problem. So we need a search pipeline to to evolve towards promising algorithms. So in this case, we present evolution of heuristics, named as EOH, which combines large language models and evolution computation for automatic algorithm design. Basically, as we have mentioned, large language models are used to generate algorithms. It is like algorithm designer. It will generate different diverse algorithms and to drive like exploration in the algorithm space. Then the evolution computation framework will maintain a population of algorithms to evolve towards ideate algorithms. So specifically, we have this pipeline. We have a population of algorithms. So here in this population, each individual is an algorithm. Okay, it's different from like conventional EA, in which a population of solution is maintained and evolved for a target problem. So here we evolve, we like it's like a high level evolution. We evolve the entire algorithm, and if you like select one algorithm from population, the algorithm can be easily used to solve a set of instances. So basically, we evolve over the algorithms, and maybe one algorithm can be represented as a Python function or maybe a program. Then we will conduct selection. We will iteratively conduct the selection, reproduction, and evaluation, the evolution process for several populations. Then finally, the algorithms will automatically improved and refined to solve target problem. So here, how do we perform the reproduction? We first select some parent algorithms from population, then we instruct large language models to generate new offspring algorithms. Okay, and here is an example. And we actually we have different prompt strategies so that we can enable exploration and exploitation in the algorithm space. Okay. And this size is the main idea of UH and the other methods along this line. And I hope you can understand the key idea. So and here is the illustration of one reproduction process in this pipeline. Okay. So we have like three algorithms. In this case, we select three parents from the population. And then we let large language models perform reasoning on these algorithms. And then we have the new algorithms and their code implementation. So this kind of prediction is used many times iteratively in the evolution framework, and we will automatically have the final good algorithms in the end. Okay. So we, as you can see, we think is like provide a new popularities and provides new paradigms for algorithm design, because conventionally when you design algorithm, right, you need a try and error process, and you need to change, you need to create new ideas and refine code, which is time consuming and tedious. And if you use other like deep learning based method, you still need the training data, right? And maybe you need to craft the deep learning framework to make it effective. But in our pipeline or in UH, the handcrafting, the human design is minimized. I will not say that we don't need a human in the loop. But the effort is minimized when compared to other methods, other paradigms. And also, we will illustrate it in the next section. We have very good results on many problems. It enjoys good automation and promising performance. Okay, so in the third part, we will introduce some case studies to help you understand how it works, and also present the platform named LM4AD, which is a fully open source and modularized to enable the usage. Okay, so firstly, here's a simple example for illustration, which is online bin packing problem. So in this problem, we have the coming boxes, and we need to pack them into, we have a coming items, so we need to pack item into the boxes. Okay, and we want to minimize the number of used boxes. And because it's online, so we don't know what kind of items will come next. So we only have one by one in one time. Okay, and what we actually consider is one-dimensional online bin packing for illustration. So in this case, we only have one dimension of items. We have a set of boxes and a set of items, and we want to pack them into the boxes to minimize the used number of boxes. So the most intuitive one, the most intuitive algorithm or most intuitive heuristic to pack is to pack them into the first box, right? And in this case, we have the solution is like this. We need 4 boxes to pack all items. Then if you have experience on this problem, maybe you tried many times, you will find a better heuristic. In this case, maybe you will not simply pack them into the first box. You will have some a new strategy, so that you only need to use like 3 boxes in the end. Okay, so this kind of heuristic or algorithms are usually are designed by human, right? So now we will let UH to automatically discover this kind of heuristics. Okay, so this is how we integrate them into EOH. Basically, we are not like design everything. Okay, we design the key steps, which is how to select the next box, right? And here's the implementation. Basically, here's the here's for LLM reproduction, and after you generate a new algorithm, you will evaluate them on like a set of bin packing instances, and you will have a finish. Then here it will be used in our evolutionary framework as we have introduced. Okay, so here's an illustration of the evolutionary process, the performance vs the number of generations. The larger the performance is larger, the better. And here we highlight some key components during the evolution which are automatically discovered. And finally, we also present the final designed algorithm or heuristic. And here we compare the algorithm to existing ones. We will find that this kind of method will automatically design the algorithm idea and the code implementation. And you can see that the code, like the algorithm, is not so like intuitive. Maybe you as even if we have experience on target problem, we need some effort for the try and error, and maybe this kind of hybrid term is not easy to design even for human. And actually here is only a simple example, and we have tested the, okay, here's the result. Our results are better than the human commonly used one, and also font search. And actually we have tested on many different problems, including like some combinatorial optimization problems like TSP. So I think of you have know TSP and CVIP or these combinatorial optimizations. So I will like focus on the results. So we compared EOH, the automatically designed algorithm, to some simple heuristic and also like OR tools. And also we compare them to the deep learning based one like POMO and LEHD. Then here's the results on some selected TSP lib instances, and the values are the gap gap to the best known solution. Okay, so we can generate 3 out of 6. We can actually reach the best known solution, which means the gap is 0 on 3 of them. And also the similar results are observed on flow shop scheduling problem. When we compared to human design heuristics like NEH and its revisions, and also we compared to deep learning based ones, we have a clear improvements on the performance. Okay, and not only combinatorial optimization, we also we have also tested on other optimization problems, optimization algorithm design tasks. And here's example on base optimization. And in this work, we only design the acquisition function. Okay, and then we compared to these classical acquisition functions such as expected improvement and its revisions. We actually we have like a better overall performance on these commonly used instances. Okay, and not only optimization. Here's an example on machine learning. So in this work, we design the acquisition. Oh no, sorry, the adversary attack heuristic. which means like, for example, here we have a panda, a photo for panda, right? And you will recognize it as a panda. But if you make some noise on the figure, the machine learning model will misclassify it as other animals or maybe something else. So we let EOH to automatically design the adversary attack heuristics to um, for the misclassification. And in this case, we also generate some interesting results we compare to handcrafted ones. And here's an example for science discovery. Okay, so basically here we design the turbulence model, the function for turbulence model. And maybe you don't need to know all the details. So basically, for example, if you want to design a car, right, you need to do a computational simulation of the car. And we have some experiments functions to be used as to simulate the turbulence in the simulation. And this kind of functions usually designed by human according to some like some proofs, and also some of them are from experience. And in this case, in this work, we let EOH to automatically design the function. And here's one of the results. We have three figures. The first one is from real world experiment. Okay, and the second one is for it's from simulation with a human designed function. And then in the last one, we are simulations with UH design function. Okay, so so in this case, our results are more like closer to the experiments. And here is the last example, which is I think is very like interesting, because we have a new world record on cycle packing, which is a classical like mathematical and optimization problem. Okay, so basically in cycle packing, we want to pack a set of cycles inside a rectangular space, two-dimensional rectangular space. And we consider our problem with n equals 26, which means we have 26 cycles, and we want to pack them into this area. Then we want to maximize the sum of their radius. Okay, so before before this year, the best known solution is like 2.634. And about around like 1 month, maybe in the last month, AlphaEvo from Google, they improve the best known solution to this one. And maybe 2 weeks ago, Express, which is a commercial company focused on global optimization, they try this problem and they further improve the results, slightly improve results. Okay, so we also try this problem, and we find that very surprising, the algorithm automatically designed by EOH can outperform all these commercial solvers and the SOTA results from companies, and improve the state-of-the-art results to a new record. Okay, and I want to highlight that we are fully open sourced, because Express, they use a commercial software. We don't know what happened inside, right? And our Evo also, they have public their final results, but they don't public their algorithm. So, but we have open sourced all the details, including the search histories of EOH. You can, if you're interested, you can find it in this link. Okay. Um, then I'm glad to introduce to you that our open source platform named LL4AD. And this best known, this world record is designed actually use this platform. If you're interested, you can scan the code and visit our web. Okay. So in this platform, I will skip this one. In this platform, we have integrated around 100 different tasks, including optimization, machine learning, and set discovery. Okay, and we have 4 sports like handbook, like tutorial, and also we have also developed a GUI specifically for our platform, and you can easily integrate different large language models. Okay, here's the doc. Okay, here's more tasks like science discovery, also machine learning, and also like here's for aircraft landing. Also OEM also design this kind of agents. Okay, we have conducted comprehensive evaluation and benchmarking to make sure the platform are like robust and easy to use. Okay, here's the results of like using different methods on different tasks, and here are results with different large language models. Okay, and here's the usage. You can simply initialize different part, and you can like click run, then it will run smoothly. Here's a GUI for the platform. Okay. Then here's the last part. In this part, we will try to fine-tune large language models for algorithm design. In the previous work, we only use pre-trained models, include like majority of papers using pre-trained models. Okay, then we will try to fine-tune large models to see whether we can have some insights on developing these domain models. So previously, the preferred works such as UH, okay, they use large language models, but they don't learn during the evolution process, during the algorithm design process. But human experts can like gain knowledge during the algorithm design process, right? So we will try to like fine-tune large language models using the algorithm design like histories or experience to answer to try to answer 2 questions. Okay, the first question is how to prepare the training data for fine-tune algorithms on algorithm design tasks. And the second one is can we use like maybe a small fine-tuned model so that it can outperform large models on algorithm design. In this case, we can reduce cost and improve the efficiency. So basically, here's how we do the fine tuning. We have 4 steps. Okay, I will not go through details due to time limit, but we have like 4 key steps. In the first step, we collect data from the search history, such as if you run UH on some problems. Then in the second step, we construct the samples using a grid-based method, and each sample, because we use the directly preference optimization DPO, so each sample is actually a pair of algorithms. So we need to construct samples from the collected data, and then we perform offline learning, offline fine tuning. Then we use the fine tuned models for automatic algorithm design. Okay, so basically in DPO, it can be regarded as each sample is a triplet, and which consists of a prompt and a pair of positive and negative completions, which are algorithms in our cases. Okay, and we propose a grid-based pair sampling method So for balance, the diversity and the quality. Okay. Okay, here's the experiment settings. We fine tune large like Llama 1B, and here's the detailed experiments. So in this slide, we show the results using EOH. So here EOH means the method with pre-trained llama model. The EOH FT fine tune, which means EOH with fine tuned model, and then we can see obvious improvement during the search process, right? And here are 3 independent runs. So there is obvious improvements in the efficiency and also the final results. We also tried on font search. There's also an improvement. And we compared the results to Llama 8 billion. You can see that on EOH here, AB means EOH with Llama 8 billion. Then our fine-tuned 1 billion model actually performs very competitive to like 8 billion without fine-tune. Okay, so we have similar results on font search. Okay, so I will see here, this is only preliminary attempts, and we have many open questions to answer, maybe whether whether GPO is the best training paradigm, right? And also, do you have like a out of distribution generalization capability to other tasks? And I think maybe this kind of works well. There will be more works to explore these directions. Okay, so in conclusion, we first present an overview of this field, which is the emergent domain, and we introduce EOH. It combines large language models and evolutionary search. We think it introduced new possibilities for the automatic algorithm design. Then we present some case study and also MFAD platform. I hope it will be helpful for researchers who are interested in this area. Okay, and we have some future direction. I think maybe I will be quick to introduce this direction. First one is domain large language models. As I've mentioned, we don't have words along this line, so maybe, but I think domain model can be beneficial to algorithm design, as we have illustrated in the preliminary studies. We can enhance a small model to perform comparatively to large models. And the second one is fitness landscape analyze, because this landscape is for algorithm space, okay? Because it's like code-based space, so we don't have much knowledge on this kind of space. Usually we search on continuous space, the black box optimization instances, okay? So in this space, we need to understand what happened, and we need to understand how algorithm behave, like LLM behave on this kind of space. And the multimodal algorithm for multimodal large language models for algorithm design is also an interesting topic, because usually when human design an algorithm, we need to observe the results, right? So if we use multimodal large language models, maybe we can have additional information on the target tasks and help the algorithm design. Then is the long code or the for algorithm design, because now we mainly focus on some components of the algorithm. When you want to design the entire algorithm, which is usually very complicated, especially for these SOTA algorithms. They consist of many functions and some complicated data structures. So to tackle this kind of work, we need to develop advanced frameworks. Okay, and here's expensive MVD because in engineering designs, many tasks are expensive. Okay, we need to explore new methods. And finally, it's the benchmark. Actually, recently there are many interesting works on this direction. And for example, Civil Bench, they propose some combinatorial operation problems benchmarks specifically for large language model based automatic algorithm design. Okay, and actually, their bench has been also integrated into our platform. Okay, okay, thank you. I think maybe we can have some questions.